All right, last time we started section 3.5 with multiplication and division algorithms. I'm just going to run through a few of them really quickly, not go in too much depth, but just remind you where we were when we left off. And then we're going to do some multiplication and division type problems. So we did the multiplication and division properties a little bit with the exponents, but the ones I want to focus on for our discussion right now are these algorithms. So we have our expanded algorithm. That's simply sort of separating out the pieces, and it looks a lot like the standard algorithm otherwise. This one's more of a visual of the standard algorithm, or the expanded algorithm, where we separated it into these sort of area boxes and multiplied. And then it's called partial products. And then we had the lattice algorithm. Again, it sort of separated things out, but then you add along diagonals when you're done, so that's kind of different. We had two algorithms for division. The standard algorithm, which you all know and love. We talked about the fact that that requires us to actually remember and have all those details correct on multiplication tables. Thank you. That's fine if you're dividing by numbers, especially by numbers that are multiplication facts that you know. If you divide by something like 14 or 92 or something like that, division gets a little bit trickier. The other algorithm we talked about was repeated subtraction. We talked about the fact that this is not terribly efficient. However, it eliminates some of the need for multiplication facts being memorized, either because students have learning disabilities potentially, or if it's just numeration facts that we don't memorize. Like I don't memorize the 14s tables, stuff like that. This is another option for division. All right, so we're going to talk about Juan. Juan saved $53.40 in 3 years. If he saved $95 per month in the first year and a fixed amount per month during the last 2 years, how much did he save per month during the last 2 years? Alrighty, so what are we going to do to solve this problem? There's several steps in this problem. This isn't just we're going to multiply two things together and be done with the problem, right? There's quite a few things going on. So somebody give me a where would you start kind of thing. The first year. So how much in the first year? What do you want to do? Okay, so it said he saved $95 per month in the first year. So we can multiply by 12 to figure out how much total he saved in the first year. All right, so this problem right here, let's do it with our standard algorithm first, and then we'll do it with another algorithm, and you guys can pick. I don't care. So what would we do to multiply standard algorithm? 2 times 5, which would give me 10. I write a 0, and I carry a 1. And then I would do 2 times 9 to give me 18, plus my 1 is 19. Okay, now either we skip the placeholder or we write a 0 in it to preserve it, either way. And now I'm multiplying the 1 times the 95, which of course is just 95. And I add the resulting values here together, and what do I get? What is it? 1140. Fantastic. Okay. If I were doing this with the, I said I would let you choose, so I should do that since I already said it. What do you want to do? Partial products, lattice, expanded? What do you want to do?
Can we do the lattice?
Sure. All right, lattice method means that I make a 2 by 2 box because I have 2 digits by 2 digits. And I write one of the two numbers, again, it doesn't really matter which one, on top, and the other one on the right. And I write single digits. Okay, that is different than the partial products method. And then I split my boxes along the diagonal, and I multiply in each box. So the first top left-hand corner would be 9 times 1, which is 9, and the 9 goes in the bottom right box. I'm going to change colors. Okay, in the right box, I have 5 times 1 is 5, so this is in the 5 right here. Bottom left box, 9 times 2 is 18, so I do the 1 in the top and 8 in the bottom. 5 times 2 is 10, so it's 1 in the top, 0 in the bottom. And then I'm using my diagonals. All right, bottom right-hand corner, excuse me, that would be a 0. Then I have 8 plus 1 plus 5 is 14, so I'm going to write down a 4 and I'm going to carry a 1. My 1 plus 9 plus 1 would be 11. So technically I would write a 1, I'd carry a 1, and I'd move it over. I don't have anything else in the next column, so it's okay if I write the 11 here at this point. Of course, the answer is still 1140. What am I going to do now that I have the 1140 by whichever method I chose? I'm going to subtract it from what? All right, so 5340 is how much he saved total. And we know in year 1 he saved $11.40. Okay? This one's actually really nice. There's no borrowing or anything going on in this particular subtraction. What do you get? 4,200. Now what? Okay, so why are we going to divide by 24? Okay. Yeah, it's a fixed amount and it's per month and there's 24 months when we're talking about 2 years. Yeah, so we're going to divide by 24. Okay, so now this would be a really good example where I don't know a 24's tables. Do you? Okay, so I'm going to do this with repeated subtraction just so you can see it being used in another context besides the one we saw earlier. So what you're going to do is you're going to subtract values of 24 that are 24 times 10. So 24, and then I've got 240. I would have 2,400, 24,000. I mean, I can keep going as big as I need. What's the biggest one that I can subtract from 4,200? 2,400. And how did we get 2,400 from 24? It's times what?
24
Times 100, right. So over here on the side, we write that this is times 100. You can either write 24 times 100, you can just write yourself down a note that it's times 100, but this one was too big, so I'm going to mark that one out. All right, so what is 4,200 minus 2,400? 1,800. And can I subtract another 2,400 from that? No. So I have to go down now. Can I subtract the next value down from that, the 240? Sure. So we're going to subtract 240, and we are going to have to subtract it several times, right? 240 is 24 times 10. Yes, so that's over here on the side. So what is 1,800 minus 240? 1,560. Can I subtract another 240? Yep. So we'll subtract 240 again. 240 is 24 times 10. What is 1,560 minus 240? 1,320. Can I subtract 240 again? Certainly. You guys are going to kill me when we're done with this problem. All right. What does that give me? 1,000 something. 80? All right, 1080? Okay. 240 again? I can. I told you it wasn't terribly efficient, right? I did warn you of that fact. All right, so what is 1,080 minus 240? What was it? 840? Okay, sorry, I just misheard. Can I do another 240? Yes, they are getting smaller, right? That's 24 times 10 still. This gives me 600. Can I do another 240? What's that give me? 360. Can I do another 240? It's my last one though, right? My last 240, that is. Oops, hang on. This is 24 times 10. Another 24 times 10. What's the value down here? 120? Okay, so I'm going to put it up here. I can't subtract 240, but can I subtract 24? Yes, I can. 24 times 1. All right, this one's not as many steps as the last one. 120 minus 24 is what? 96. Can I subtract 24? Yep. What do I have? 72. Can I subtract 24? I'm so close. I'm so close I can taste it. Can you? What is this one? 48. Come on, calculator. All right. Oh, we're almost done. 24 times 1. Over here. That's 24, right? Last one? 0. You don't always end up with 0, just so you know. In this problem, the way it was sort of described, we expected probably that we are going to end up with 0 because we are saving this amount for specific months and all that kind of stuff. But you could end up with a remainder. So let's figure out how we figure out the answer with all this work. Well, we add up all the things that we multiplied by. That's all these numbers. So there's a 100. What else is there? There's 7 tens, so that's 70. And how many ones? Is it 5? So this is 175. And that's actually the answer to the question that was posed. How much money did he save per month the last 2 years? $175 per month. Okay, any questions on that one? Okay, let's take a look at the next one. Dan has 4,520 pennies in 3 boxes. He says there are 3 times as many pennies in the first box as in the third box, and there are twice as many in the second box as in the first. How much money does he have in each box? This feels like it should be in chapter 1, right? Problem solving. What would you do?
I would have the third box be x, and then the first box would be 3x, and the second box would be 6x.
Okay, so you've got 3 boxes, right? You told me your third box was x. What else did you tell me after that, Amy?
Well, the first box is 3 times the third, so it would be 3x.
Okay.
And then the second box is twice what the first one is, so it would be 3 times 2 times x, which would be 6x.
Right. Okay, is everybody good with where all those values came from? Okay, so we've got 3x, 6x, x. Everybody good with that one? And then what would you say next, Amy?
Well, all of them added together would be 4,520. So 10x equals. Third box would have 452.
Okay, and so did you divide to get that, Hannah?
Yes.
So you divided by 10. So x ends up equaling 452. Let's go back and actually make sure we got the directions part too. So it says, the directions actually say that the question they ask rather is how much money does he have in each box? So this is 452 what? In the third, in pennies. So how much would it be if we were actually writing it? I mean,
$4.
yeah, we probably would write it as a money amount in dollars. We probably wouldn't write 452 cents. I mean, you could. It'd be a little bit awkward. So box 1.
Oh, that's box 3.
Thank you. Box 3. That's what I meant. Yeah. $4.52. What about box 1 then? It'd be that times 3. Okay, so this is kind of where the algorithm comes into play, right? Is that we're actually multiplying the 452 times 3 now. So let's do partial products because we haven't done that one yet. So I'll just use the number 452 for now, and then we'll turn it into dollars when we're done. Okay, so we'll use the whole number 452. So if we're using partial products means writing out the 452 as 400, 50, and 2. And then you're drawing a grid. Now, because I'm only multiplying by 3 here, my grid's not very big. It's just a 3 by 1, because one of them has 3 digits, the other one has 1 digit. But I can multiply all the pieces out the same way. So what's 400 times 3? 1,200. What's 50 times 3? 150, and 2 times 3? 6. So if we're looking at these added together now, 1,200 plus 150 plus 6, what do I get? 1,356. So in terms of money, what would that be in box 1? $13.56, cents. And then our last one is box 2. And for box 2, what are we going to have to do? So we could take, like Amy said, we could just take the 1356 times 2, right? Or what could we do? Yeah, you could take the original 452 times 6. Either way, right? But the second box is double the first. So I kind of like the idea of taking the 1356 and multiplying by 2. So let's do this with a standard algorithm this time. So let's take the 1356 times 2. So 2 times 6 is 12. Write the 2, carry the 1. 2 times 5 is 10, plus 1 is 11, so we write the 1, carry the 1. 2 times 3 is, plus 1 is 7, and then 2 times 1 is 2. And then in money amounts, what would that be? $27.12. All right, any question on that one? Okay, a little bit of a number theory. That is what this course is called, right? Number theory. Number theory fact going on in the next one. A student observes that 39 plus 41 is 40 plus 40. That's true, right? They took one away from one, added it to the other one. We had a name of that called trading off when we've seen it before. And they want to know if you multiply 39 times 41, will that one also equal 40 times 40? So that's the first question is, does it work? And the answer is actually no, never. It's not even a not always. This one won't work. What happens if you try it with these particular numbers? What do you get? That's true. So like there's zeros at the end of 40 times 40. There's a 9 at the end of the other one, right? Because you have 9 times 1. What are the actual values you get? Let's just write it out real quick. What is 39 times 41? 1599. And what happens when we do 40 times 40? 1600. So clearly these are not equal, right? So write yourself down a response of what you would tell the student. I mean, you're going to show them this. This would be a fact that you would probably want to show them, right? And to talk about the fact that this is not going to work. But the student might want to know, well, are they always going to be off by 1? Because that's a nice feature. Like if I am going to want to multiply 39 times 41, and I can do it as 40 times 40 instead and just compensate, you know, add 1, subtract 1, whatever it takes, that'd be pretty nice, wouldn't it? It would. It would be an interesting feature. So for right now, the answer to the student's question is no. So write down no and write down a response to tell them why. What would you actually say to them? Are you guys about done? Telling them what's up? Explaining what's going on? Okay, so if you flip your page, you'll see where I was headed. Another student observes that 39 times 41 is the same as 40 times 40 minus 1. He also found that 49 times 51 is 50 times 50 minus 1. And he wants to know if the pattern continues. And if it does, what is the relationship that has to happen between the first two values, right? Like that's asking about these two. Hang on. Like these two values compared to these two. What's the relationship that has to happen to make these things hold? So what do you notice between the examples that the student picked?
Like 39 and like a 9 and then a 1.
There's a 9 and a 1, all right? What else do you notice? They picked the number like between the two numbers, right? Okay. How far apart were the numbers that they originally started with? 2, all right? So if they're wanting to know, does the pattern continue, we at least want to start our focus on having numbers that are 2 apart. Is everybody good with that? So that there is the one number in between that we can use on the other side. Is everybody good so far? So the relationship with the number 39 and 41 is that they're 2 apart. Okay? So when it talks about what does the relation have to be, well, so far, all we know that the relation has to be as we're looking at this is that they would have to be 2 apart to continue a pattern. So let's see what happens if they are 2 apart. So let's consider two values that are 2 apart, but they're general values instead of specific values. So in general, we're talking algebra. I mean, that's what I mean by saying general values. Whatever I have for one value, I have 2 more than it for the other one. So x and x plus 2. They just differ by 2. Right? Now, if I have x and I have x plus 2, what's between them? X plus 1. So this is the one side of the equation. The other side of the equation would be x plus 1 and x plus 1 and minus 1, according to what the student is sort of seeing, right? You got the two numbers multiplied on the left, you have the number in between them multiplied by itself, and then minus 1. And the question is, do these two things equal each other all the time? And we're going to do just a tiny bit of algebra to see whether or not it works. So what happens when you multiply x times x plus 2? You have x squared plus 2x. Okay, so that's a distribution property of whole numbers, right? Just like that. On the second one, when you're doing the distribution here, you have to remember that you have several distributions. So here's the first distribution, x times x, which gives me x squared. Then we have our outer distribution, so the x at the front at the 1 at the end gives me plus x. We have our inner distribution, so I have 1 and I have x, which gives me another x, or 1x either way. And then I have our last piece in the distribution, which is 1 times 1, which gives me 1. And then I still have this minus 1 here at the end that I have to include, right? Simplifying and so forth. What does this give you? X squared, what's next? Plus 2x. It's the same, isn't it? These work. The only condition that I had as I was working was that the numbers were 2 apart, so that I'd have 1 exactly in between. Now you might have to decide, well, what would happen if I still had something in between, but maybe they were 4 apart and there were 1 in between, or 6 apart and there's 1 in between. That's a little bit different discussion. We're not going to go down that bunny trail right now, but that might be where the student would go towards next, especially if you said, yes, it will always work if they're 2 apart. And so is that inquisitive student potentially going to say, well, what if they're 4 apart? They might. And if they did, what would you do? You'd work it out, right? You'd use an x and an x plus 4, and what would be halfway in between? X plus 2. And you could simplify to see if the pattern would continue, or if not, how it was different than the ones you already had. So the only condition that we had here is that this works whenever the numbers are 2 apart, or differ by 2, or something of that nature. So it isn't even so much the fact that the number in between was a multiple of 10. The ones that the student picked weren't they? Right? 39, 41, 49, 51, right? They picked numbers that were sort of surrounding a power, not a power, but a multiplication product of 10s, right? We don't even need that. We could use, say, 34 and 36, couldn't we? They just have to be 2 apart. Any 2 apart will work. All right, the last part of this section has to do with mental math and then estimation. So we're going to start with mental math. So again, this is the stuff you do in your head, but you have to write something down on paper so I know what's going on in your head, right? Okay, and we're doing it with multiplication here. So the first example is 46 times 5. So this is called front-end multiplication. Front-end multiplication means taking the first digit sort of as its whole number, by itself part, 40, is 40, and multiplying it by 5, which gives me what? 200. And then taking the second digit as a single value by itself in its place value, which is 6 times 5, which gives me 30, and then adding those results together to give me 230. So you're simplifying the multiplication to be multiplication as 1 digits. That's what you're doing. Okay, 1 digit multiplication, and you're adding it together. Front end means you're starting with the front. Go off in here. I need my jacket back, or my sweater back on. Okay, so this is front end multiplication. And you do it with everything. So like, let's say it were a 3-digit number. Well, you'd have to do it 3 times, right? So if you had, like, say, 462, you'd have to do 400 times the 5, 60 times the 5, and then the 2 times the 5. All those pieces. All right, our next one is compatible numbers. So we had a compatible number strategy before. We grouped things together that added together nicely. Well, now we're going to group things together that multiply nicely. And there are things that multiply more nicely than others. In particular, I like multiplying 4 times 5 better than 4 times 8. Why? But what makes it clean? It gives me a multiple of 10. That's what makes it clean. So compatible numbers give me multiples of 10. And there's several things that we could have used here to do that. We could multiply the 4 times the 5, We could multiply the 8 times the 5. We can multiply the 2 times 5. It doesn't matter. You just have to pick. So I already picked these two just a moment ago, so I'm going to continue to pick them. So 4 times 5 would give me 20, right? What else would be nice to pick? Sure, we could do 5 and 2 if you'd like. 5 times 2 would give me 10. And then my last thing that I didn't get in there yet was the 8. Right? So and then 20 times 10 would give me 200. And 200 times 5 gives me, oh, I'm sorry, I left out that, you're right, that's 8 at the end, not 5, I'm sorry. 200 times 8 then would give me 1,600. So the fact that commutativity works with a multiplication is a very useful fact. Use it to your advantage. Switch the orders around of things. Associative as well, move things around. All right, I absolutely love this one, and students forget this one frequently on the test when I've asked questions before about this one. This is thinking money. I know I already did 46 with front-end multiplication, and that's fine. We can do it that way. But thinking money is very friendly. So when you're thinking about the values of money that you have pennies, nickels, dimes, quarters. Those are your basic ones, right? So a dime is worth 10 cents. A nickel is worth 5 cents. It's a lot easier to multiply by 10 than by 5. Are you guys with me? It is. It's a lot easier to multiply by 10 than by 5. So one way to think about this 46 times 5 is to think of this as 46 nickels. I would prefer not to work with nickels. I would prefer to work with dimes. So if I have 46 nickels, how many dimes is that? It's 23 dimes. So what you're really doing is you're changing the currency that you're working in from nickels to dimes, which is essentially multiplying by 2, and then you're changing the 46 by dividing by 2. It's kind of like trading off, right? Multiply one piece by 2, divide the other piece by 2. But you're doing it in terms of money. You don't even think about it this way when you're doing it. You're just thinking about what you know about money. So 23 dimes, how much is that? $2.30, or without the dollars and cents, it's $2.30. And you're done. Money is fantastic. This one, though, you might be thinking, okay, but I did 46 times 5 with the front-end multiplication, and I liked that way anyway, so what's the point? Well, it's even more useful over here. I really don't want to multiply 45 times 25. That is a 2-digit multiplication problem, isn't it? Truly. But if I think about this instead as 44 quarters, and I think about the relationship of quarters to what? Pennies or dollars, depending on which direction you go, right? I think I'm going to go with dollars. So how many quarters are there in a dollar? 4. So how many dollars is 44 quarters? It's 11. It's $11. Okay, so that's $11, but kind of like what Amy said, this is in cents, essentially, kind of what we started out with, because we just started with 25, not 0.25 or something like that. So if I talk about $11, how much money is that now? Well, it's $11 like this, but we were working with whole numbers and stuff before. This is 1,100 cents, because originally the 25 was in cents. This is 1,100. And I didn't do any long multiplication in there at all, did I? Much preferable. Okay. 2 more, and then we've got some estimation. Breaking up the dividend. These are both division ones now. All right, so we have 6318 divided by 9. Okay, so it's nice sometimes to break up and to notice, if you take a look, 63 as a number, 18 as a number are both divisible by 9, right? So what I'd like to do is, instead of, I don't want to write 63 and 18 because I do need to preserve the place value they are, but I can break this apart into 6,300 and 18. Does that make sense? So if I divide this now as 6,300, and I'm just going to put a vertical line kind of in between them and the 18, and I'm dividing them both by 9, what is 6,300 divided by 9? 700. Remember, this is stuff you'd normally be doing in your head anyway. And then what's the 18 divided by the 9? 2. So what is this value? 702. And that's probably pretty close to what you would have done in your head anyway. You wouldn't have written in this at all, but that's how you probably would have thought about it, something of that nature. You have to be careful, though, because like the number 425, there is a nice way to break it apart, and there is a not so nice way to break it apart. Somebody tell me a nice way to break apart 425. 425, like that, right? What would be a not so nice way of breaking it apart? It would still work, it just wouldn't be very friendly. 420 and 5. So this one's called compatible numbers because there is a very nice option of those two. And there's one that's really just, you wouldn't do that. You shouldn't do that. It doesn't make any sense to. So you have to think really clearly about what makes sense to break these apart into by compatible numbers. So then we can divide by 5. So what's 400 divided by 5? 80. And 25 divided by 5? 5. So the grand total would be 85. Yeah? It's good? Okay. Our last two are computational estimation, okay? Please, when you get to the test on Friday, please be careful not to estimate when you're supposed to be finding things exact and vice versa. Highlight, circle, underline, whatever it takes to make sure that you're using the right method for what you're being asked for. So on these, we're asked to use estimation. And the reason I mention this specifically is because you see the word front end, and we've seen that before. We've talked about front end before, but we've talked about using it exactly, not with estimation. So I'm going to show you how to use it with estimation now, okay? We did front end estimation last time as well when we did addition and subtraction, so I'm going to show it to you with multiplication. Front end estimation looks a lot like the front end method that we used before. We're going to multiply the first digits together. We're just not going to multiply every single digit times 4. We're just going to do the first two. So we're going to use the 3, we're going to use the 8, and we're going to ignore the 6. We're going to sort of, in essence, take the 6 and round it off to a 0. We're ignoring it. We're just doing 2 digits. So if the number were in the thousands or the 10,000s, you just use the first 2 digits of that number. I don't care what the number is. So this would be 4 times 3, 300, which gives me what? 1,200. We would have 4 times the 8, which is 80, which gives me 320, and then we add those together, which gives us 1,520 as an estimate. So this is approximately 1,520 using front-end multiplication with estimation. So front-end estimation. It's just the first two. No matter how many digits are there to start with, just the first two. And if you kind of think about it, that's really about all you can do too much of in your head to begin with anyway, is a couple of them. Okay? So the goal with estimation is to make it easier to work with. Then we're going to do compatible numbers. 4,132. Our goal is to pick another number close to 4,132 that's much easier than that one is to divide by 4. 4,000 works just fine. Ashley got it, yeah. So we're just going to estimate this to be 4,000 divided by 4. And we're going to get that this is approximately, right? We're doing approximations here. Use those approximate symbols. 1,000. It's an estimation. It's not meant to be exact or precise. It's meant to give us an approximate value. And that's all you're looking at. Okay? Any questions? Yes?
On like problems like this, since it is technically like supposed to be in our head, you don't care if we don't set it up like in the normal division thing? We can just put like the little division.
Yeah, this is fine.
Okay.
But I need to see something about how you're thinking about it. Yeah, but this would work for sure.
Okay.
Your goal was to do it without anything, have to write anything down. So this would be just fine.